Hello and welcome to another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 6, Lesson 3 on average rate of change. We know already that this unit is all about functions, and functions are all about inputs and outputs. And average rate of change, obviously, is going to have something to do with how fast those inputs and outputs change. So let's get right into it right away. You will want to have a calculator handy for today's lesson because we're going to be just doing some routine calculations, but certainly ones you're not going to want to waste time on by doing by hand. Now, when functions increase or decrease, and we saw that in the last lesson, we want to know often how fast this occurs. We're going to do that by using the tool of average rate of change of the function. So let's start off by taking a look at a function that's pretty easy to get a grasp on. Exercise number 1. The number of people who have entered a concert hall was measured as a function of time since the doors opened. The data is shown in the table below. Letter A, at what rate in people per minute did the hall fill up in the first 4 minutes? All right, so rates are certainly not something that are foreign to you. You've been dealing with ratios and rates since probably about 4th or 5th grade. So I think this first problem is pretty easy. At what rate in people per minute did the hall fill up in the first 4 minutes? So obviously at 0 time, there are no people in the hall. That's kind of the idea of 0 time. Then at 4 minutes, there are 48 people in the hall. I'd like you to pause the video now and figure out at what rate people entered the hall over those first 4 minutes. Pause the video now and take a little bit of time to figure that out. Also, make sure to include proper units because the units are key when we look at average rate of change. All right, well, if 48 people entered over 4 minutes, then it makes a lot of sense to just do 48 people divided by 4 minutes. And of course, 48 divided by 4 is 12, and that's 12 people per minute. All right, you can actually use the word per, but what you're going to find in 8th grade and above is that most of the time, units will now be expressed in sort of fraction notation, if you will, where you want to always read the numerator at first, people, you want to read the fraction bar as the word per, and the denominator then per minute, right? So 12 people per minute. And that makes sense, right? 12 people per minute are coming in, so there's 12 people, then 24 people, then 36 people, then 48 people, and your 4 minutes are over and we're up to 48. Now that was pretty easy because at time 0, there were no people in the room. But let's take a look at letter B. How many people entered the hall between 10 and 15 minutes? Now this is actually kind of a critical issue, right? At 10 minutes, there were 144 people in the hall. At 15 minutes, there were 239 people in the hall. So how many people must have entered the hall between 10 and 15 minutes? Pause the video now and see if you can figure that out. Well, hopefully it makes sense to just take the 239 and subtract the 144, right? Because that's going to tell us how many we'd have to add to the 144 to get up to the 239. So the number of people that kind of went into the hall during that time will be 239 minus 144. That's where I like to just have my calculator handy so I can just immediately 239 minus 144, right? And that means that 95 people entered the hall during that time. Okay, so 95 people came in. Now let's take a look at letter C. At what rate did people enter the hall in people per minute, just like letter A, between 10 and 15 minutes? All right, well, we know that 95 people entered the hallway between 10 and 15 minutes. We also know that 5 minutes elapsed between 10 and 15 minutes. So see if you can use those to figure out at what rate people entered the hall from 10 to 15 minutes. Pause the video now and try to figure that out. Not that I have to do this, but just to be clear, right? I kind of want to know how much time elapsed, which we can obviously just do that in our head. But if I couldn't do it in my head, I'd sort of take my 15 minutes minus 10 minutes and get 5 minutes. That would be the amount of time that went by. I could then say, well, 95 people entered into the hall in those 5 minutes. Right? Now I can do my division, which always gives me a rate, 95 divided by 5. And that tells me 19 people per minute entered the hall during that 5-period span. Now, side note, right? Just think about this for a second compared to our answer in letter A. It means that people are entering the hall more quickly between 10 and 15 minutes than they did in the first 4 minutes. In the first 4 minutes, the rate that they entered was 12 people per minute. But between 10 and 15 minutes, they were coming in at an average rate of 19 people per minute. Finally, letter D. Was the rate in C greater or less than the rate that people entered the hall between 15 and 18 minutes? All right, so now, bring this up so that we can see the table down here. Now you got to kind of figure out how fast they were coming in from 15 to 18 minutes. Pause the video, see what you have there as a rate, and then compare it to what you had in C. Well, let's first figure out how many people just came in between 15 and 18 minutes, right? We know at 18 minutes there were 275 people in the hall. At 15 minutes, there were 239 people. So the first thing I'm going to do is just figure out what 275 minus 239 is, right? That's going to actually be, I think, 36, but let me just make sure. Right, we've got 275 minus 239. Yep, so 36 people entered the hall. And of course, the amount of time that went by, not that I really need to do the subtraction here, is going to be 3 minutes. So again, think about this. 36 people entered the hallway in 3 minutes of time, right? Between 15 and 18 minutes, 3 minutes of time go by. 36 people came in. So the rate that they came in was 36 people per 3 minutes. And I can do that 36 divided by 3 in my head. I'll get 12 people per minute, right? Which means that the rate in C was greater in C, right? In other words, people are coming in faster between 10 and 15 minutes, 19 people per minute, than they came in between 15 and 18 minutes, 12 people per minute. And it kind of makes sense, right? If you ever think about like, all right, I'm going into like some kind of concert hall or something like that. The doors open, maybe people are coming in slowly at first, then maybe they're coming in faster and faster, and then they slow down as it gets closer to when the concert or play or whatever is going to start, right? So you might think, okay, the rates are going to go up at first, then the rates are going to kind of come down, okay? So that's it, right? Now, hopefully, this is a really simple idea, right? If I want to know how fast the output is changing compared to the input, well, first I have to find out how much did the output change? 36 people. Then I really have to kind of figure out how much the input changed. 3 minutes. Then I have to divide the two, how much the output changed compared to how much the input changed, and that will then give me a rate in blank per blank. In this problem, it was always in people per minute coming into this hall. Let's now use this to formally define the average rate of change. All right? The average rate of change can always be calculated by taking the change in the output, right? In that last problem, it was the people who had entered the hall, divided by the change in the input. In our case, that was time. All right? Now, I want you to really look at that formula, and let's talk about exercise number 2. The formula to calculate the average rate of change of a function is identical to what formula that you have already learned. In other words, this is exactly the same formula that we saw just 1 unit before for some other thing. What did this calculate in the last unit? Well, it calculated the slope of a line, right? This is just the slope of a line. Now, that doesn't mean we can't use this formula when what we have isn't a slope of isn't a line, okay? And I'm not saying we're calculating necessarily the slope of a line in any of these situations, but it's the same calculation. And think about what the slope of a line always was. It was always how fast is the y on the line changing compared to how fast the x is changing, right? That's still a rate, right? And that's what we're getting here. If I find how much the output changes, how much the input changes, and I divide the two, then I get the average rate of change, which again is exactly the same as finding the slope of a line that connects those 2 points. Let's work a little bit with average rate of change. All right, exercise number 3. A ball thrown into the air is thrown into the air such that its height is a function of time since it was thrown. The data is given in the table to the right. Letter A, find the average rate of change from 1 to 3 seconds in feet per second. Show your calculations. All right. Now, this one's pretty easy, but let's kind of think about it from this perspective of slope of the line, right? So from 1 second to 3 seconds. So really, we've got 2 points, right? Kind of 2 coordinate points. We have the point 1, 91, and we've got the point 3, 167. Okay? So the average rate of change, what I'm going to want to do is I'm going to want to take this and subtract this, and then I'm going to want to divide it by this minus this. So literally, the change in the height, I'm going to use h for height, divided by the change in time is going to be 167 feet minus 91 feet divided by 3 seconds minus 1 second. All right, so let's figure out what those two are separately, and then we'll do the division. All right, so I've got 167 minus 91, and that's going to give me 76 feet. I'm going to run out of room here. 3 seconds minus 1 second, I think I can do that without any other help. And now I can do 76 divided by 2, and I'm going to get 38 feet per second. All right, simple enough. And again, this should look very similar to how we calculated the slope between 2 points that lied on a line, all right? And again, all we're saying is that for every second that goes by, right, the height of the ball is increasing by 38 feet. Now, let's take a look at B, which can get a little tricky. Find the average rate of change from 3 to 6 seconds in feet per second. Show your calculations. All right, so now I want to go from 3 to 6. All right, let's write down those 2 coordinate points, maybe give myself a little bit more room. You know, I've got 3, 167, and then I've got 6, 41. So my change in height divided by my change in time is going to be 41 minus 167 divided by 6 minus 3. I'm leaving the units off for right now. Now I have to be very careful. I understand that it's very natural to always take the smaller number and subtract it from the larger number. But I always have to be consistent. This minus this divided by this minus this. Now you could do this minus this, but then you'd have to do 3 minus 6. And again, either way it's going to work out fine. But now let's, just like before, do this on the calculator, right? I've got 41 minus 167. And that's going to be negative 126. Now I'll probably put the units on, feet. And of course we've got 3 seconds. So I'm going to just divide that by 3. Hopefully, there we go. And I get negative 42 feet per second. And boy, is it important that you have that negative on there. Let's talk about why in letter C. Why is the average rate of change positive in A, but negative in B? All right, think about that a little bit. Look at the table, right? This is just time, 0 seconds, 1 second, 2 second, 3 second, 4 second, 5 second. Here's the height of the ball, 5 feet above the ground, 91 feet above the ground, 145 feet above the ground, 167 feet above the ground, 157, 115, 41, right? Why is the average rate of change negative from 3 to 6, but it's positive from 1 to 3? Sorry, from 1 to 3. Why is that? Pause the video and write down just a real-world explanation for it. Well, it's pretty clear to me. The height is increasing from 1 to 3 seconds, and then it's decreasing from 3 to 6. And boy, is that important, right? That is the whole kind of point here. So the height is increasing from 1 to 3 seconds, but decreasing from 3 to 6 seconds. And that is what the sign of the average rate of change will tell you. So if the average rate of change is positive, that tells you that the function is increasing overall on that interval. And if the average rate of change is negative, that tells us that the function is decreasing. The values are going down overall on that particular interval. So if we had made a very, very understandable error and done 167 minus 41 instead of 41 minus 167, we would have gotten a positive here as well. And that would have told us that the ball was actually going up from 3 to 6, literally gaining 42 feet in height for every second that passes. But in fact, it's gaining 38 feet per second for every second that passes from 1 to 3, and then it's losing 42 feet per second for every second from 3 to 6. All right? So the sign on the average rate of change is extremely important. Positive tells you the function is increasing. Negative tells you that the function is decreasing. Critical. Let me bring this over here and let's take a look at one last one. Now, calculating the average rate of change from a table is pretty easy because we can just kind of grab the values right out of the table. Here's my input, here's my output, okay, now I can do my change in inputs, my change in outputs, etc. But sometimes we're asked to calculate the average rate of change when we're given formulas. And that's always harder because we have to actually calculate the outputs. We have to use the formula to come up with the outputs. And then once we have the outputs, we can then find how much the output has changed, divide it by how much the input has changed, and get our average rate of change. So let's take a look at that with a couple formulas in exercise number 4. Two functions are shown below. Determine which function has the greater average rate of change from x equals -2 to x equals 4. Show the calculations that lead to your result. All right, great. Well, let's do it. Let's figure out the average rate of change for function A together and then have you work on it for function B by yourself. And then we'll kind of do the comparison to see which one's got the greater average rate of change. Now, all we know are the inputs, x equals -2 and x equals 4. But the whole point of a function is given the inputs, the function rule better tell us the outputs. If it doesn't, it's not a very good rule, or at least it's not a very clear rule. So let's come up with the outputs, all right? So when x is equal to -2, the output for this function will be 10 times -2 plus 3, which will be -20 plus 3, and that'll be -17. For x equals 4, the output will be 10 times 4 plus 3, and that'll be 40 plus 3, or 43. Okay. So now we can actually calculate the average rate of change because we can calculate how much the outputs have changed divided by how much the inputs have changed. And again, we have to be rather careful here. All right, change in y divided by the change in x, right? We can kind of think of this as x1 and x2, y1 and y, let me put it here, y1 and y2. So I'll do 43 minus negative 17, that's how much the y's have changed, divided by 4 minus negative 2, that's how much the x's have changed. 43 minus negative 17, you could do that on the calculator. I'm going to just go ahead and do it in my head. That's 60. And then 4 minus negative 2 is 6, and 60 divided by 6 is 10. So the average rate of change of this particular function is 10. What I'd like you to do is pause the video now and figure out the average rate of change of this function, and let me just say it's not going to equal 3. It's not like we can just pull some random number out and throw it down as the average rate of change. So why don't you do the same, figure out the outputs when the inputs are negative 2 and 4, do the change in the inputs divided by the change in the outputs to get the average rate of change, and then we'll compare them. Pause the video now. All right, let's go through function B. Let me just kind of move this out of the way. So I'll give myself a little extra space here. When x is equal to negative 2, all right, my y is going to be 3 times, that doesn't look like a 3, 3 times negative 2 squared. That's going to be 3 times 4, which is 12. All right, when x is equal to positive 4, my y is going to be 3 times positive 4 squared. That's going to be 3 times 16, which is 48. All right, now we can calculate our change in y divided by change in x. That's going to be 48 minus 12 divided by 4 minus negative 2. 48 minus 12 is going to be 36. 4 divided by negative 2, 4 minus negative 2 is still positive 6, and 36 divided by 6 is 6. All right, so we have an average rate of change of 10 here and 6 here. Again, understand what that means, right? Because we don't have any per units right now. We don't have any feet per second or miles per hour or anything like that. Literally what this means is that for every 1 unit here that x goes up, y goes up 10 units. Over here, for every 1 unit that x increases, y increases by 6 units. This is literally 10 units of y per unit of x. This is 6 units of y per unit of x, and therefore function A has the greater average rate of change, which was ultimately what this problem asked us to determine. Which one has the greater average rate of change? It's function A. All right. So functions are all about sort of the interplay between inputs and outputs. And we know functions can increase and functions can decrease. And when I say functions can increase and decrease, I'm really saying the y values can increase and decrease as x gets larger. All right? The question is, how fast do they increase and decrease? And the way that we measure that is simply by finding how much the y values changed divided by how much the x values changed. And yes, that is exactly the same formula as the slope of a line, because that's what the slope of a line is. It's the average rate of change on a line. The only thing about lines is that their average rate of change never changes, right? Their slope is their slope. Other types of functions, the average rate of change will actually change. Anyhow, we're going to work more with average rate of change as we move through this unit. For now, I just want to thank you for joining me for another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.